Hi all, this is Susanta again, and I'm going to do a lecture here on how we can design a VCO. Previously I've actually gone through one of the lectures. A lot of you have looked through it and has given me really good comments, and I'm really encouraged to do more in this area. Is that on the CMOS LCO VCO? Okay, CMOS LC VCO design. That's what I will do, but that one covered the industrial aspect of how we actually design these VCOs and all the various factors that are normally not there in the textbooks when you go to college. So hopefully I've learned a lot. I know some of you have given me really good feedback on it, and that's why I thought when you learn it from the books and then also some of the aspects that I've tried to capture in my other video, it's all good. You get to learn a lot. But if I tell you that, hey, design a VCO for me, show me how would you do an initial design on paper, a first cut design with some hand calculations, how would you do it? Most of the time we are at loss. I've gone through that experience myself, and I've developed a method which I'm going to share with you. Feel free to use it if you like it. If not, you can still hopefully learn a little bit out of it. This is a method that I have come up with where I don't want to jump to the simulator directly. I want to come up with a simple method to design a circuit on paper, do some hand calculations to get some W over L values, inductor values, capacitance values, and etc. as we'll go through. And this example is geared towards that. So in this case, what I will try to do is we'll try to do this example where we'll try to design a VCO. It's an LC VCO, which will look kind of like this. We'll go through it, but just to tell you what I will try to do is, one of the things which is critical in the VCO is when you design it for a particular tuning range, so that you can tune the VCO. So in this example, I will try to use some of the values as noted here, where the VCO can oscillate at a maximum frequency of close to 6 GHz. Even though I'm targeting 6 GHz, as I'll show in the example, my initial calculations won't push it to 6. It's almost to 6, but not all the way. But let's just put it as specifications that we want to design a VCO with an F max of 6 GHz and F minimum, the minimum oscillation frequency of about 3 GHz. Why I chose this range is because in the cellular world, which is where I come from, when you design these oscillators to cover most of the cellular bands in the world, the highest band being close to 2.7 GHz. And if you normally we never use the VCO frequency, we'll always have VCO divided by something, okay, like a divide by 2 or divide by 4 or divide by 6 factor to derive the LO out of it. So coming back to the highest frequency in cellular world of about 2.7 GHz, if you multiply it by 2, you will need a VCO of about 5.4 GHz. So I just kept it as around 6 GHz as a number, being the maximum frequency. Lowest end of the cellular spectrum, if you look at it, there are 700 megahertz bands, the LT bands in US, which are very popular. So if you wanted to use a divider ratio of 4, it would bring you close to about 3 gigahertz. Okay, in most applications you don't use a divider ratio of 4, you use 6, so you are comfortable in this range. But this range, kind of, if you can design a VCO in this kind of a range to cover almost all the bands which are there, the cellular bands, you would also cover Wi-Fi being another important application. Wi-Fi is 2.4 gigahertz, or twice of that is 4.8 gigahertz, so that will be in this range. So this example I chose to see that how we can cover most of the cellular bands in the world, and also Wi-Fi and maybe many other applications using this VCO. Not that it's not meant for one size fits all, but still we'll just target this as the values. Let's not worry about phase noise for now, because phase noise, the noise, it's better to leave it on the simulator, derive it. But before I go to the simulator, can I actually do a VCO design as shown here, topology that I've discussed before on paper using some hand calculations? That's what it's targeted for. Okay, so here is the topology that we have seen previously. We'll have some sort of a bias current. I'm showing by a current source, but it could be also a PMOS current mirror here, which will be pumping some I bias into it. Then we will have this stage, which is what I'm calling as a core. This is the CMOS core. It has got cross-coupled NMOS devices and cross-coupled PMOS devices. What I want to do is, before jumping into the simulator, I want to know what would be the starting values for W and L. What should be the W and L values for this PMOS? What should be W and L for this NMOS? I want to know some values without actually before if I don't do it, I have to go to the simulator blindly and put some values, and I don't know if I'm starting at a wrong foot, or it's better to calculate some initial values. So I want to know them. So A and B are the oscillator nodes. Between there would be an inductor. I want to know, okay, what should be the value of the inductor. I just don't want to blindly guess it. I want to know something, so we'll hand calculate it. There will be a cap bank, which will be a discrete bank of many capacitors, which I'll show you in just a minute. And there is a varactor, so I want to know more details of how that cap bank will look like. The varactor, what should be the approximate value of the varactor. Then mostly, if this is the oscillator between A and B, if you do voltage at A minus voltage at B, you will get a sine wave. But most of the time we don't use sine wave, we square it up. So here are simple inverter type buffers that are used to square it up and provide square wave output at VOP and VOM, which are driving some load capacitances based on your design, based on your chip. So we also want to know what should be the W over L sizes for these buffer stages. So I want to have an initial design for the core. I want to have initial design for the buffer also. Okay, along with cap bank and all. And since we are talking about cap bank, the cap bank, what I'm going to use in this design is it's an 8-bit binary cap bank. The smallest branch being what I'm calling as C unit. This is mostly going to be a metal cap. Then you're going to have some sort of an NMOS switch of 1x size. So 2 C units are in series, so the effective smallest capacitance becomes C unit by 2. Okay, so this is my smallest branch, or the LSB. The next one is 2x. The capacitances are 2x, the switch size is also 2x. The next one will be 4x, 8x, 16x, and also if you have 8 bits of control being you're controlling this bit here. So with this LSB bit, you're controlling whether you can turn it on and off. With the second LSB, you're controlling this branch to turn on and off. So finally, this becomes the 8th bit, or 2 to the power 8 is 128. So these things will be like this. So just as a starting, we are just going to use an evenly scaled binary of 8 branches. So we'll have 8 bits or 255 tuning codes here discretely that you can tune. This is kind of similar concept to what my other lecture goes. That's why I've tried to use this same example. So if you've seen that other lecture on CMOS VCO LC VCO design, this is compatible to what we covered there. So this is what the cap bank will look like. So I would like to know what should be my C unit value. What value do I start with? What should be my switch size? I want to know some initial values before jumping to the simulator. Then comes the inductor. So inductor in this case, if it's L, right, it's going to have some losses based on its finite Q, which we can model as RP, which is roughly equal to L times omega times Q. Omega is the frequency of oscillation at that point. We have a wide range, so omega is going to be different. As we said, we're going to go from about roughly 3 to 6 gigahertz. So this is different value. And we are also going to have Q, which will vary, okay, over this frequency range. But at different oscillation frequencies, this RP value is going to be different. And along with, whenever you make an inductor, when you synthesize an inductor in all these tools that you have, the inductor synthesis tools, peak view, EMX, and all these momentum, they always have a self-resonant frequency. Okay, so that self-resonance frequency is captured by another parameter that I used. Because when I put an inductor, what I'm trying to do is I'm trying to put a simple inductor, and doing hand calculations, I don't want to use complicated model. I want to use a simple model of an inductor with some loss, which is modeled like this, and a capacitance, which is dependent on the self-resonant frequency of the inductor. For example, if this is trying to, and I think I use it as, I'm trying to oscillate this at around, as I said, 3 to 6 gigahertz, and I assume that it has its own parasitics, which is this cap, where this will have a self-resonance at 20 gigahertz. I think that's what I used, like 4 times of a resonant frequency. That may not be true. That may be true based on how the inductor is synthesized, but we are not getting into those details. We are trying to put something in to do some initial hand calculations in a simple model. So that's what the scope of this lecture is going to be, is given this core, given this different models, how can I come up with some initial calculations on the paper based on, this is what I'm trying to do. I'm trying to see if I can oscillate at 3 gigahertz and all the way up to 6 gigahertz. So that is kind of the goal of this design exercise. Now before we go there, we also have to calculate a lot of capacitances, because without these capacitances, we cannot really do this exercise. And these device capacitances will be dependent on your your process. So in this case, I don't think I mentioned anywhere here, but I'm trying to use some device capacitances from a 65 nanometer process. Okay, I've used some of these numbers previously in another lecture where I tried to do a design of a 2.4 gigahertz LNA. I think I used some of these numbers there, and that's why I'm trying to use the same numbers here. And I'll just try to use the same thing. So there are lots of device capacitances which comes from the process foundry, but there are only some of them that I will use because it's not possible to use a lot of them in HAL calculations. The first one is the overlap capacitance, which we call a CGSO or CGDO. So this is the overlap. So if this is a MOS device from source to gate, there is an overlap capacitance when this device is off. Okay, so we always see this. So CGSO and CGDO are normally they are mostly equal. So this is the overlap capacitance, and the way we will estimate this overlap capacitance is we'll use a value. Okay, I made a mistake here. I want to correct this. I have this value here is called as 0.5 femtofarad per micron width of the device. It's actually not 0.5, it's 0.3. I think previously I've used the value of 0.3. That is typically how much the process foundry can get. So I'll use the example number 0.3 from now on. It's just that I have a wrong value here, and I apologize for putting a wrong value, but hopefully you will remember that it's a 0.3, not a 0.5. So it is given as 0.3 femtofarad per micron. What does this micron means of width? So if you have a device which is a 10 micron wide, okay, irrespective of the length could be the smallest length, bigger length, or whatever. But if it is 10 micron wide, you can take 10 micron multiplied by 0.3, which will give you 3 femtofarad. So that 10 micron device will have a CGSO value of 3 femtofarad and a CGD value of 3 femtofarad. That is how it's specified. It's always specified per micron, which is the width of the device. So it scales linearly with the width of the device. So this is what we call as the overlap capacitance for the MOSFETs. We will need it. The next is the oxide capacitance. So we always have the overlap, but along with the overlap, now what happens is this device, has an oxide here, right? The gate oxide. So that gate oxide is normally specified as a density in micron square. Okay, so what it means is, the total oxide capacitance, if you were to do, it will be this value called Cox times W times L. That will be the total capacitance. We always specify, the foundry will specify Cox as a value, as I'm going to use here, is 15 femtofarad per micron square. So this is the oxide density, and this value is pretty close. It may not be 15, maybe a little bit here and there, but we'll just use this number for 65 nanometer. So micron square is, so if you want to know the actual capacitance, you have to multiply with W and L. W in micron and L in micron. That will give you the total capacitance. But remember, you cannot use the total capacitance all the time, because when you have this device in saturation, if you remember, at the CGS side, you only see 2/3 of that value. So Cox times W times L gives you the total capacitance here, and this is actually CGS, which is 2/3. And CGD, you will only see the overlap capacitance because the channel is pinched off. If you remember from the previous, the MOS fundamentals of MOS and operation, so we will have that part there. Now, if this device was not in saturation, but it was in active region, then CGS, you will see half of this total capacitance. Cox WL, this total parallel plate capacitance, you will see half of it on the gate to source side and half of it in the gate to drain side. Okay, so I forgot to write here CGS and CGS here, but these are the values of CGS if they're in saturation or inactive. So these two parameters are important. The overlap capacitance in the technology, you have to have some idea about it. Without that, some of the hand calculations I'm going to do are not going to be valid. So you have to know this number. So here we'll use the overlap capacitance as 0.3 femtofarad per micron square, and the oxide density Cox as roughly 15 femtofarad per micron square. So that's what we are going to use. And let me take I just need to take a quick break. I'll be back. Next, what we need to look at is, we have seen the capacitance values from the process, so we need it. So we did that. Now what we want to do is, a simple question to ask is, how much GM is needed to oscillate? Remember, in this structure, if I go back, what these cross-coupled devices are doing is, they're trying to create a negative resistance to overcome the losses of this everything else, like the Q of the inductor, maybe loaded Q of the cap bank and all that. So this cross-coupled GM, PMOS stage is creating a GM, NMOS stage is creating a GM, so they both are creating negative GM trying to overcome. So the question to ask is, how much negative GM do we need, right, to overcome these losses? So we need to have some idea of that. So to get an idea, what you do is, I will assume that the PMOS scaled is roughly twice the size of the NMOS, such that they both have almost equal GM. It is not going to be always true, but it's a good assumption to have when we start. So I can call this as the PMOS is giving GM of core, which is the PMOS, and the NMOS is also the same. So together what we have is, if you do the series resistance of the two, and again these values are going to be negative if you find the negative, because it's creating a negative resistance, that will be 2 by GM of core. Okay, so I want to know what is the GM of core value approximately I need so that I can overcome the losses on this inductor. So what is that value? We're going to calculate it, but first let's look at the inductor. So inductor is going to have an RP, right? The parallel effective resistance is given as L times omega. Omega is 2 pi f frequency of oscillation times Q at that frequency. Okay, Q is also not fixed, but it's also dependent on the frequency. Now, if you look at this formula, what you will find is in most of the inductors, if you are actually at a lower frequency, which is what I've seen as F min, then the Q of the inductor is also low. Means that the inductor is more lossy at lower frequency. Most of the time when we synthesize the inductors, we will say that, hey, we want to go to 6 gigahertz. We will synthesize an inductor to have a best Q around 5 and 6 gigahertz, somewhere around there. But if you were to come down to 3 gigahertz, its Q is actually going to be lower. Okay, so it is more lossy. So here what I'm doing is I'm trying to find the RP value at the lower end of the frequency, because that's where this RP value is going to be minimum. Why? The RP is L times omega. Omega is 2 pi f min. Okay, f is smaller. Q is also smaller at this lower frequency. So overall the RP value is going to be a smaller value. So whenever you have a smaller resistance in parallel with this, that means that is much more lossy. Remember, if RP value was bigger, then I don't need a lot of negative resistance to overcome this RP. But when this RP value is smaller, I should have enough GM, enough negative resistance in the circuitry to overcome that lower RP value. Otherwise, it will not oscillate at the lower end of the VCO. So that's kind of what I use is I go to the lower end and then I try to find where the losses are maximum, and from there I will try to derive this thing here, which is, as I said previously, since you have two GMs in series, the total effective negative resistance could be assumed as approximately 2 over GM core, which is what I've written here. It's of course a negative sign, but I'm not using it because that negative resistance is trying to overcome this RP. Okay, and this negative resistance actually should be less than the positive resistance for it to oscillate. Otherwise it will not oscillate if RP is actually more dominant, right? So from here you will get a formula of the core should be RP by 2. RP is at the lower end. I will use the lowest value, which will give me the maximum GM. And what I use typically is, even if I get a GM value, and as I will show in the calculation later on, which is basically, I have an Excel file I prepared and I put in all these values and will calculate all this. There, what I do is, I don't use just that value of the GM. I would go ahead and use like more than that, because it's always good to have more GM than what you have just designed for. I just use a 2x value and that is the kind. But this gives you an idea that, okay, if I know the value of RP, which I can calculate this way, what should be the GM that I need? Okay, so I will go through that when we go to the table, the Excel file. So this answers the question, how much GM is needed to oscillate. If you don't have enough GM, that guy is not going to start oscillating. Okay, it will not oscillate, it will just sit there. Then as we go through the Excel file later on, we'll also calculate many capacitances. If we have the core, and this is the core of the VCO, and by core I mean is this guy. Okay, remember this part, which is the cross-coupled NMOS and cross-coupled PMOS, I'm calling as a core, and this stage I'm calling as the buffer. So for this core stage, I want to calculate what are the various parasitic capacitances which end up being very dominant. Okay, so we need to know some estimate of what are these parasitic capacitance values are. Okay, we need to know that for core as well as for buffer. That is what we will try to calculate next. because see, you have found GM, so you can say, you know what, I can get a particular GM by pushing certain I bias. You can make an assumption on I bias and get some W over L values, so that for those I bias by 2, you can get a particular GM value, right? So you can calculate W over L's based on what GM you need. But once you know the W over L's of this course, now you also need to know what are the parasitic capacitances associated with it. So that's what we will kind of go through. So let's just I think when I go to the Excel file, it will become more and more clear, but I just want to go through these different aspects first before we jump into the Excel file, so that you don't get confused too much of, you know, where did these calculations or formulas came from. So in the core, when it's oscillating, I'm going to consider the case at 0 crossing. So as I said, A and B are the oscillator nodes. Normally, if you take voltage at A minus voltage in B, you're going to get a sine wave. But right at the sine wave, I'm not going to consider the peak of the sine wave, whether it's the positive peak or the negative peak. I'm going to consider the 0 crossings, which is where the voltage at A and voltage at B are 0. I mean, they are equal, sorry. Voltage at A and voltage at B are equal. So VAB, the difference is 0. So that is the 0 crossing of a sine wave. That's where it's more susceptible to noise and everything. And I will use that point to estimate some of the parasitic capacitances. Okay. So if this voltage is 0, you know, you have some voltage, they are in full VGS, so they remain in saturation. All these 4 devices at that point are in saturation. So if I consider a single node, say node A, what do I see here? I see a CGS of this PMOS device. Also I see a CGS of this NMOS device, right? Then I see a CDS. Okay, I think I made a mistake. I'll correct it. There's a little problem in the formula here. Then I see a CDS of this NMOS device, and I also see a CDS of this PMOS device. Okay, so if I want to know all the capacitance at one node, a single node, okay, what will it be? As I said, CGS of the PMOS, which is here. Don't worry about this half term right now. CGS of the PMOS, then I have CGS of the NMOS, then I see CDS overlap, right? CDSOP means CDS overlap here for this guy, because this guy is in saturation. So drain to source, you will only see overlap. This and this. What is the mistake here is I actually see 2 of them. So there should be a factor of 2 here and there should be a factor of 2 here. Why? Because see, if this point is A, this B, they are inverted. So when you have inverted, so if this was some voltage V, this will be minus V. You actually see twice of this because of the Miller effect. That is the part I missed here when I wrote this formula. I think I have the correct formula in my Excel sheet, but when I wrote this I missed it. So again I apologize for that. So please note that there is a 2 here and there is a 2 here with this overlaps. Okay. Then I have half of this because see, I'm calculating. So this whole term inside the parenthesis will give you the total capacitance, single end capacitance to ground. But if I want the differential capacitance across this inductor, right, that will be half of it, because you know there are 2 of them in series, and that's why I have this half term. Also I have a note here that I've only considered CGS and CDS only. There are many other capacitance, like if you consider this drain, there is capacitance from drain to bulk and all. Those things get a little more trickier to handle in hand calculation, so that's why I'm trying to avoid it. I'm just trying to only consider the gate capacitances and the overlap capacitance. Just 2 things, because anyway this is a hand calculation. It's an approximation to a first cut design. Then we'll put in the simulator, and then we'll tweak the heck out of it. But for now, this is good enough. So hopefully now it's clear all the capacitances and how we will calculate it. Remember again please that there is a 2 here for this overlap capacitances. So this is for the core. We need this capacitance because all these capacitances will go across the inductor to determine what is the frequency of oscillation. Okay, and if it's swinging differentially, I've put this as AC ground, both the sides as AC ground. Now this is at the 0 crossing. Remember, if it was not 0 crossing, and since these are in saturation, that's when they inject the most noise. But if the sine wave was at the peak, right, at that point what will happen is these devices will be in triode. They are driven into extreme triode region, and if their RONs are really small, they don't really cause much noise at that point. So the noise is really caused at 0 crossings, and Also at the zero crossings, the capacitance is the most, and that's what we will use in our approximate calculations. Remember, as these nodes are swinging, A and B are swinging, the capacitance of this device is changing. This device is going from saturation all the way into active or off, right, based on as we looked in the other one. So this is not a constant capacitance, this is a time varying capacitance, but to do a simple hand calculation, this gives you a good estimate. How about the buffer? So after this core, at each of these point A and B, we have a buffer. So I'm just showing like a B side of it. A will have the same thing. You just have a simple inverter buffer to take the sine wave and square it up here at the output. So there, the capacitance that you will see are, again, you're going to see CGS values of N and P, and also the CDS, the overlap values of N and P. So you have two CGS, CGS of P and CGS of N, and then you have the two overlap capacitances. You again do half of it because this is single-ended. This term is single-ended. We do half of it to get the differential capacitance. So across this inductor, you're going to get all this capacitance from the core. Across this inductor, you're also going to get all this capacitance from the buffer, which is approximated by that. So these are the simple equations we will use to estimate capacitances. And then I think we have the cap bank. So we will also have to estimate the cap bank, that when a cap bank is on, how much is the capacitance. When the cap bank is off, how much is the capacitance. So this takes a look at it that way. So again, we have the nodes A and B, and I'm only showing, so there are 8 such branches. I'm only showing the LSB branch, where we said that there are 2 unit capacitances called C unit. I want to calculate this from my hand calculations. There is a switch here whose W over L also I want to calculate. And how would I do it is, so when the switch is on, its on resistance is assumed to be very small. So the total capacitance between these nodes is C unit by 2. Okay. So any branch that is on, we take half of this 2 capacitance that is there, that becomes the capacitance. But when a switch is off, then what happens is we have C unit, and this MOS device is off. When this MOS device is off, we have this overlap capacitances, CGSO and CDS, they are equal. So this becomes approximately more like this. You have a C unit, then in series CGSO to some sort of a ground. This could be a strong ground or a weak ground if this gate is driven by like a high resistance value to isolate a ground from here, whichever way. But effectively it becomes a series of C unit and this overlap. Same thing on the other side. Most of the time your C unit is much bigger than this guy. Like the overlap capacitances, the parasitic capacitance is very, very small, especially true in this fine geometry process. So if you're using 65 nanometer, 40, 45 or 28, whichever you use, these assumptions are very true. So all this capacitance you can estimate as between A and B, you're going to get the overlap capacitance divided by 2. So the capacitance of a branch, if it is on, is this, and if a branch is off, it's this. Remember, we are going to have 8 branches. Many of those branches will be on, many of those branches will be off. So what we want to know is, if a certain branch is on, what should be the capacitance of the branch, and if a certain branch is off, what should be the capacitance there. Because all that capacitance all add up in parallel across this inductor, which determine that what is the frequency of oscillation at that point. So that is for the cap bank, and now that we have done it, let me go to the Excel file that I have prepared, and let me see, yeah, here it is, Excel file, and try to go through this. So all these concepts that we talked about, how we can do some simple hand calculations to do design, that's what is here. This Excel file, again, I have a comment in the very beginning because there's no way for me to share this over a video. But if you like the approach that I show you and you want to get access to this Excel file, the simple Excel file, just send me an email here. Here is my email address. Hopefully you can see it all right in the video. And if you drop me an email, I will send you this simple Microsoft Excel file, so you can play around with it. So that's kind of the idea here. So here we will go through all these different fields one at a time and see how we can calculate, what is the F max and what is the F min. You can see that these values are way off right now. It's showing F max as 7.5 gigahertz and F min as 5.3 gigahertz. That's not what we want to design because I have some values, but I will walk through each of them and then it'll give you a better understanding of what's going on in this Excel file. So now that we have gone through some of the theory part of it, let's try to go through the spreadsheet that I was talking about. So I'll try to go through all the different fields that I used to make this simple, initial design of the VCO, and we'll try to correlate each of these different things with what we talked about in the notes. So again, if you would like to have the spreadsheet, just send me an email here, sushantasengupta1976@gmail.com, and I'll forward this to you. Or you can even build it up yourself. After we've gone through all this and all the theory, it'll be pretty straightforward for you to build it also. So first of the design targets, as we talked about, we want to have the Fmax of the VCO to be 6 GHz and Fmin is 3 GHz. These are some two values that we are trying to target. Whether we will be able to get it or not, we will see. And at the end, here it does a few calculations and it comes up with the Fmax and Fmin values. Don't worry, they're off right now because I've just put some random numbers to start with, and we will see how different things we are going to play around. The next set of fields that we have is the device capacitances, the parasitic capacitances. The overlap capacitance that we told as CGSO, CDSO is the gate to source and drain to source overlap capacitance. As I mentioned, I'm using this for I took this example. I did this in a 65 nanometer process, and there the value is roughly about 0.3 femtofarad per micron width, and that is what I do, because when I get these values, I go and I put it in the simulator and I run it to see that how close are my hand calculations to what Fmin and Fmax I will actually get at the end, and if it's close enough, that's good. That tells me that this process of doing an initial design worked out, which in this case it did, and it has actually worked out a few times for me, in different technologies. But this specific example is just for the 65 nanometer, but the same thing could be applied to other technologies also. So if I come back to, if you remember, as I was doing the device capacitances, as I mentioned, I made a mistake of using 0.5 here, writing 0.5. It's actually 0.3 femtofarad per micron is the value that I used in this calculation here. The gate oxide, as we say, Cox is the oxide density of the gate, which is so many femtofarads per square micron, because you have to multiply this number by W and L of the gate to get the total parallel plate capacitance there of that gate. Okay, so that is the next field. Next I have the field for the inductor. So any of these values here that you see in bold, like the L is in bold and I have this thing highlighted in yellow, this is what I'm calling as one of the variables. I want to tweak these variables and see how these different things are changing. And when you do an initial design, you can also make these as design variables and tweak them around to get your performance. So that's what I mean by putting bold values with and highlighted in filled up with yellow. So for the inductor, I'm just using an initial value of 1 nanohenry. It could be anything, but let's just put this value. We will change it and we'll see how these things move around. The Q that I have assumed at Fmax around 6 GHz, I'm assuming that I can make a coil which can give me a Q of 12 at Fmax, which is 6 GHz. The resonance frequency, as I mentioned earlier, I'm assuming it to be 20 GHz. If I'm trying to make a coil with a Q of 12 at 6 gigahertz, I might not get 20 gigahertz. It all depends on what kind of technology you have and what are the parasitic capacitance and all. 20 gigahertz of self-resonance might be a little bit too high. It might be 12, 15 gigahertz. So it doesn't really matter so much. But for now I'll just go ahead and change it. I'll just put it as so maybe realistic number is 15 gigahertz. Okay, so if I change it, then what it does is it calculates a capacitance, parasitic capacitance value. And what is this? Let me go to, where was it? So we covered here, we said that based on the self-resonance frequency, we are going to have a parasitic capacitance here and an RP, right? So this parasitic capacitance C underscore par underscore L that I used in the notes, I try to use the same value, and the value comes to about 112 femtofarad. Okay, for this value of L. If I change the L to say 2 nanohenry, you will see that value will change to give you the self-resonance at 15 gigahertz. Okay, so this parasitic value will keep changing based on whatever the value of the L is and whatever the value of the resonance is. So I'm making the value of the L as a variable, but I'm not making the resonance. I'm just saying that maybe the resonance just stays around 15 gigahertz as we are putting it. So this computes that. Then is RP. Now here I'm computing RP at F min. Why? Because as I mentioned that if you go, okay, let's see, where was that? Okay, here it is. Yeah, RP. RP is L omega times Q is roughly the value of RP. And L times 2 pi F. F, if I take the minimum frequency, that's when my RP becomes less, means the inductor has more losses. And at that point, the Q is also small, so that also has a double impact. Okay, double punch, and makes the RP really small. So I'm calculating the RP at F min, and it comes out. So what I'm doing here is, you can see C11. What is C11? C11 is the value of the inductor. So L times 2 pi. Okay, C5 is F, which is the CF min. Okay, C5 is F min 3 gigahertz multiplied by C12. C12 is, so this is the maximum value of Q, which is the Q is 12 at 6 gigahertz, but I'm scaling it down to 3 gigahertz. C5 by C4 is, the scaling down. So if the Q is 12 at 6 gigahertz or 3 gigahertz, I'm just doing a linear scaling for a simple approximation. Of course, it doesn't scale linearly, but here the Q will become, from 12 it will go down to 6. So that is an overkill. Oh, I mean, that's too pessimistic of an assumption, but still. So I'm using based on this simple calculation, I'm using a value of Q of 6 at 3 gigahertz. But in reality, you will have a better Q than that. So your RP will be higher than that. But based on that, I'm calculating that, okay, this could be the worst case pessimistic losses of the inductor. So I have to calculate the GM to overcome these losses. I have to have enough current into the oscillator core. I have to have enough device sizes to be able to overcome this, okay, these losses. And based on, as we talked about previously, the GM that I do is just, I just take this RP value and I reverse it. And as I said, I am not just trying to overcome this RP losses only. I'm trying to make the GM bigger than that. So I have an extra factor of 2 here. Why did I put it? If I just put just the amount of GM that is needed, for example, GM core should be RP by 2. Okay. Okay, something is wrong here. It should not be RP by 2. It should be 2 by RP. I think I just messed up this formula again. But here, this formula is correct. So it says, okay, let's see, something is wrong here. So this is going, okay. So here is the formula, 2 by RP, which is 715. And of course, I'm converting it to millisiemens. That's why I have 1000 multiplied. But whatever the GM it says, I have actually doubled it to, I doubled the value here to make sure that I actually have more GM than what I really need. Because if you just design it for the edge, this is hand calculations, it's not really going to cut it. You need to have a little margin. So the margin I'm putting here is, I'm saying that I will just go ahead and double it up. So I probably needed, about 18 millisiemens. Rather than that, I just said I'm going to do 36 millisiemens as the GM that is needed for each of them, like the PMOS and the NMOS of the core. Now that if we have done the inductor, we come to the VCO core. Okay, so we're going to go and design this core. The core has the PMOS devices and the NMOS devices. How do we find the approximate value for W's and L's and also the bias current, okay, to get the GM? So I'm again making an assumption that bias current coming from the top is 5 milliamp. Again, this is an assumption, it's a variable, you can change it. I'm also assuming that, let's just say W value for the NMOS. So before W, let's see L. Since I said 65 nanometer, the L is 60 nanometer roughly it comes. Okay, in whether it's TSMC or Global Foundry, you will get a value of 0.06 micron, which is 60 nanometer. So the L, I kept it as minimum. Now for the W, I said, okay, how about if we put a value of 25 for the NMOS and 50 for the PMOS? If I do that, I see that the GM, okay, is going to come roughly around 30 millisiemens. How do I get GM? GM is, again, if you remember the other notes that I had, it's 2 times K prime, okay, W over L times I, right? That's what is going to give you the GM. And with that formula, the K prime value that I'm using for an NMOS is 200. For PMOS, I'm using 100. So if I use that formula, I will get this value of GM that is going to come. okay, because this is the formula in saturation, 2 times K prime W over L times I and the square root of this whole thing. Okay, now since you can see that it is not good enough, so this is giving 35, I'm getting about 30, it's probably better for me to go ahead and increase this, because if I push 5 milliampere and if I have the NMOS as 25 by 0.06 and the PMOS as 50 by 0.06, it may not be enough to make it oscillate at the F min part. The losses may be just at the edge and over corners. See, we have to also design it very robust. We have to design it over temperature, corners and all. It might not really work so good. So what I will do is, this values is not giving me the GM that I need from my initial calculation. So I'll just go ahead and boost it up. I will boost it up more by saying, okay, I will not boost up the current, but let me just go ahead and boost up the device sizes. So I'll make the NMOS to be 50 micron and accordingly scale the PMOS to be 100 micron. It doesn't have to be 1 to 2, but most of the technologies it's about, PMOS to NMOS ratio is about 2. Sometimes it's 2.2, sometimes 2.5. This is just, again, an initial thing to put in and see, how much it would give. So if I do that, it boosts my GM to roughly 40 millisiemens, which is more than this. So this is probably a good point to start with. Okay, there is always margin there. We are putting more and more margin to make sure it will be a robust design over temperature and process. Now as you make the devices bigger, the capacitances will become bigger. It will have an effect on your F max and F min, and we will see all that in a minute. But right now this is only trying to look at, do I have enough negative resistance for that bias current to be able to overcome the losses of the inductor. That's the only thing I've done here. We will iterate this also in this once we have gone through one round of all the variables, and then we'll iterate and see how F max and F min work. Okay, let's see what else. The core. Now, how do we compute these capacitances here? Okay, so we went through this exercise of calculating the core capacitances. As I said, at each point you will see CGS of P and N, and then you will also see twice of CDS, because the Miller effect, because the voltage at A and B are equal and opposite in polarity roughly. Okay, and so that formula is put here. If I put this thing, you will be able to see it's all in there, and this is the correct formula. Okay, so what it is doing is, if an NMOS has a value of 50 micron, it's calculating the overlap by looking at this, right? 0.3 times 50 micron will be the overlap capacitances. If I want to know what is the value of the CGS, right, for the NMOS, that will be 2/3 of, let's just take the first term, 2/3 of C9 and C19. C19 is the NMOS and C9 is this, so it's multiply this, and then we also have C21. C21 is the length here, right? So CGS will become, since it's in saturation, 2/3 of W times L times Cox, right? This will be one of them, and then there is the other one, and we are taking half of it because I'm finding a differential capacitance. As I mentioned, this gives you the capacitance from A to ground, but I'm finding the capacitance from A to B, which is across the inductor. Okay, so that way with this formulas will come here, and if you change your W's here without changing L, if you change your core size, your GM will change automatically. The formulas, this capacitance will also change, and that is actually used in the calculations later, so which we'll go through. So hopefully this is clear how the VCO core is set up to calculate the effective GM roughly, and the parasitic capacitances. Same thing with the buffer. The buffer also, I'm assuming again that the NMOS size is say 25 and the PMOS size is 50. Okay, just as an assumption. What does it really depend on? See, the buffer size is going to depend on this. Where is that picture I had? See, you have the VCO nodes here, right? The oscillator nodes. Then you have a buffer, and the buffer is going to drive a load capacitance. So really this buffer size is going to depend on how big is this load capacitance. The more bigger this load cap is, more longer is this line, or more bigger are the next stages you drive, all that will determine what is this load capacitance. That will have a direct effect on this, how big this buffer has to be to drive it. Okay, so here I'm not talking about any load capacitance as such. I'm just making an assumption that some value, like if the value of the W is 25 micron, NMOS, and PMOS is 50 micron, and the lengths are 0.6, maybe it's good enough to drive the load, whatever it is. I don't know the load yet, and I have not. So if you finally put all these values in simulation, you find the load capacitance is bigger. That means the buffer is not able to drive it with sharp rise and falls. Then you will increase this. As you change this capacitance will change, and that will be affected here in this Fmax and Fmin calculation. So this is set up to calculate again what we talked about, all the CGS and overlap capacitance for the buffer, and then plug it in here so that it will show that how the Fmax, how the frequency of oscillation is moving. Okay, so this part takes care of the VCO buffer. Then what do we have next? Next we have three more things: cap bank, varactor, and routing. Let's start with the routing here. So what the routing does is, when you put this inductor, you put a cap bank, varactor and all, and when you tie it to this core, there is always going to be routing in the layout, and there are always going to be finite extra capacitances here because of all the parasitic routing, metal routing that is going to happen. So how much? So we are always going to have some parasitic capacitance between node A and B. That is what I'm calling as the routing capacitance, and I've assumed it to be 100 femtofarad differential. That means each of the nodes A and B could have up to 200 femtofarad, which is kind of on the pessimistic side. You could do better than that, but still it's good to just have a little margin while you're doing some initial design, because things only go bad at the end. So if you have some margin here in this estimation, you made it a little more pessimistic, you have room to improve it or give that margin to some other guy who's going to come and kill the the margin. So the parasitic routing is assumed here to be 100 femtofarad differential or 200 femtofarad single-ended. The varactor, I've just taken an initial size based on my experience and all, is 25 femtofarad. Typically the varactor size is chosen based on what kind of kV number do you want. Okay, if you have a higher kV, then this size has to be higher. It automatically gets bigger. But if you have a lower kV, the varactor value gets smaller. I mean, at least in this one and other designs, based on the value that I've used, is somewhere around 50 femtofarad or less. Varactors are good enough. They give a kV of about 50 to 100 megahertz per volt. I just put a number there. Again, this is a variable. You can change it. It will change all the stuff here, which we'll show in a minute. But again, what should be the varactor size? It will really depend on the relative size of varactor to the total capacitance that comes because of cap bank and everything, and how it affects kV. That part is not included in this initial hand calculations. That is something that we have to iterate a few times in simulation. Okay, but for now I've just put a value which works, which is what we're just going to use in this example. The final one is the cap bank. As I mentioned, if you go to the cap bank, as I'm treating here, is built up of 8 binary branches, as we talked about. So what is the smallest unit cap, and what is the device size that we're going to use? That is captured here. So this gives a unit size, which I'm saying that let's just assume this unit size is 5 femtofarad. Okay, these are mostly metal capacitance, whether these are MIM cap, fringe cap, or any other kind of metal, means very linear capacitances. And second thing is with smaller bottom plate. So the bottom plate capacitance is also important. So the unit value I've used is 5. We'll change it to see how it affects Fmin and Fmax. So that is the cap bank size as a variable. Then for the switch that is there in between the switch here, what is the size? The length is 0.06 minimum length, because as I said, it's 65, I'm assuming. The width is 1 micron. I says, okay, if I have a width of 1 micron and length, let me just assume 1 micron. Okay, for now. Let's see, for just this branch itself, okay, we are not worried about other branches. Other branches are 2x, 4x, 8x scaled version of this. So if we just do one thing, we can scale it around, and that's what I'm doing here. So what is the on capacitance that we're going to see differentially between A and B? It will be roughly half of this unit capacitance, right? Because there are two of them in series with a switch, and if we say the switch on resistance is really small, it's a good switch, then effectively the capacitance is this much. That's what I'm going to assume. And when the switch is off, then we see a lot of capacitances, as we did earlier. And what we said is, so when the switch is off, based on our simple calculation, it's basically the overlap capacitance divided by 2 is what we found, which is the first term here. But there's another term I have added is, what happens is, one of the things that I did not have here is, see, when you make a metal capacitance, the C unit is a metal capacitor. It will have some parasitic cap from here to ground. That parasitic capacitance could be anywhere from 2 to 5% of this unit cap. Why? Because those are the parasitic, the top plate and bottom plate parasitic capacitance that you can't avoid, and they're just going to be there. So if it is there, then we have to add that also to this extra capacitance that is coming, and I've just used in this calculation as 5%. Since it's 2 to 5%, let me just take 5% of that value and divide it by 2 because it's differential. Okay, so this way I'm calculating simply what is the on and off capacitance of the unit branch. So this is only the 1x branch. If you have the 2x branch, it will be twice of this, 4x, it will be 4 times of this, and so on. The other thing I also need to calculate is, I assumed that the switch size is 1 micron. If I have a NMOS with a switch of 1 micron and the length is 0.06, is its R-on going to be small enough? Because remember, when this switch is on, there is an R-on, and that R-on along with C by 2 causes the Q of this branch, right? So the Q of this branch should be high, it should not be lossy. So to calculate the Q, what you do is you find the R-on of the switch. So the R-on of the switch is what I'm finding from, this is the formula that I used. Since this is going to be an active region, the equation for the drain current is given as Kn prime W over L VGS minus VD times VDS. Now if you find the R-on, which is VDS by IDS, it will come out as this. You can assume Kn prime to be about 200 microampere per volt for an NMOS. You have the W over L VGS minus VT. So let's see, what did I use for VGS minus VT here. I've used 0.5 volts. Okay, so just that same formula, I put it here with a VGS minus VT of half a volt. Because the threshold voltage is 1 volt and this is like a 1 volt or 1.2 volt design, VGS minus VT is going to become roughly half a volt, and that gives you an R-on of this. Okay, so the switch has an on resistance of this. But what is the Q then? So at F max, where the Q is going to be the worst, at higher frequencies the losses get higher and higher. You know, the Q is basically going to be, this is the lossy part. This part is going to be 1 over where is the capacitance? The capacitance is C27. C27 is right here. Yeah, so half of that of the C27 that we are going to see. So what we are basically doing in this formula is, you have an R-on, you have the total capacitance as C by 2, right? And the Q is 1 over omega C R-on. Okay, so the denominator has 3 terms: omega, C unit by 2, and R-on. If you put that and you take an inverse of this, like 1 over that whole term, that gives you the Q of this branch. So with this formula, I'm trying to calculate the Q of the branch to make sure that the Q is big enough. So Q is about 18. So if this branch or any other branch which is scale branches were to be on, Q of 18 I think is probably okay to work. You can get a little more if you want it. All you have to do is increase the W, because if you increase the W of this of the unit cap, it will increase your capacitance, but it will also reduce your R-on, and it will increase your Q of the branch that is on. Okay, so this is how we can change it around and see that we are able to get reasonably good Q and also the capacitance. Of course, all these capacitance will get plugged in, which we have not talked about yet. So let's talk about that now for a minute. Okay, so here I'm trying to calculate F max and F min after having gone through all these calculations, and hopefully I have not confused you too much that how all these different things are coming, and we are considering all of that in our calculations here. The first thing I've got here is called CT code. What is CT code is, remember we said there is an 8-bit code, right, of the cap bank. So cap bank has 8-bit, 8 such branches, and it's an 8-bit code. And the code could be, if it's all zeros, then I'm assuming that all this bit coming here is 0, this is 0, this is all a 0, so all of these branches are off. So CT code of 0 means you're going to get the least capacitance from this bank, or you're going to get the maximum frequency. Okay, so this is not CT code 0. I'll tell you why it's 31. I use just doesn't have to be 31, but why don't I use a 0 here? So when the CT code is lower, you try to hit higher frequencies. When the CT code is higher, for example, if I said all these bits were 111, the maximum value could be 255. 8 bits, it could be 255. All these caps will be on. Then you get the maximum capacitance. That means you have the minimum frequency, right? So a lower value of CT code means higher frequency. A higher value of CT code means lower frequency. It's kind of opposite. Some people will do a swap of it to make sure that they don't have a problem in the loop, the PLL loop. But anyway, just for this example, I'm just using it. You can change it around if you want. So let me explain now why I use the codes 30 and something like this. So if what happens is all these calculations, the overlap capacitance and everything we did and all these things, this is for typical process. Normally there is always going to be a process shift. So when you have a process shift for slow corner, the whole frequency range goes down. So for example, if you are able to meet 3 to 6 gigahertz in typical corner, if you go to slow corner, all these numbers will scale down. Down means 6 might become 5.5, 3 might become 2.5. Now if you go to a fast process where the MOS devices, capacitance and all are fast, all these numbers move up. So since this hand calculations and also the design that you do in the beginning is for, the typical, you want to have some margin at the lower end to account for slow corner, and also at the higher end to account for the fast corner. So it's because of corners, what I do is I do not want to meet this range 3 gigahertz to 6 gigahertz using all the 255 codes. I will only try to design it to meet this range with some codes to spare on the lower end as well as some codes to spare on the higher end. How many codes do you want to spare at the lower end and how many do you want to do at the higher end? That's all based on the process, that how much the process shift is happening and all that. But typically what I do is, if you leave 30 codes, around 20 to 30 codes, so that you don't use the code 0 to hit Fmax, but you use a code like say 31 in this case I'm using. Okay, then you have left 31 codes to cover for the process shift that will happen. Okay, so if at 31 code you hit this Fmax and your process shifted, whether it's slow or fast, you can still have a code which is not 0, okay, not the extreme code, but maybe 10 or something, with which you can hit the same number, okay, when the process shifted. So what I'm trying to say is, when you do typical design, you have a code range from 0 to 255. Don't use that whole range to design for this whole frequency range. Okay, use only a part of that CT code range, which in this case I'm saying 30 to 224. So whatever the minus is, you can see. So I've left 30 codes at the lower end, 30 codes at the higher end to account for process shift in the oscillator frequency over process shift in the capacitance values, process shift in the and also the temperature part also. Okay, so that's why I'm not using 0 and 255. I'm using around 31 and 255 minus 31. So if this is my code, okay, so as I said, CT code lower means I should get a value. How is this frequency calculated? So core, so what is the parasitic capacitance of the core? We have it here, so it's plugged in. What is the parasitic capacitance of the buffer that's plugged in? Now on branches and off branches. Remember, it has got 8 branches. Some of them are going to be on, some of them are going to be off. So the on branch is basically based on, how many are on, 31 times this is on, and how many are off. Off is going to be, basically 224 times the off capacitance. So the off capacitance is here. So remember, in the unit cap size, we calculate what is the on capacitance and what is the off capacitance. If a branch was on, it was 2.5 based on this 5 value, right? 2.5 multiplied by 31. Equivalently 31 are going to be on. It's binary, it's not thermometer code, it's binary, but still if you multiply 31 times 2.5, you will get this on capacitance number. Similarly, you have 224, which is 255 minus 31, 224, right? This term here is 224 times the off capacitance, which is this one. If you did that, you will get that. So that gives you the total capacitance of the cap bank, the on part and the off part. Okay. Varactor capacitance we assume 25 femtofarad, that is there. Parasitic route 100 femtofarad we assume, that is there, right? Because we assume that varactor and parasitic there as it is. And then the inductor, whatever based on the 15 femtofarad resonance frequency, whatever it calculated, right, based on the L value, it is there. And if you take all these capacitances, right, all the parasitic capacitance as well as the capacitance of the cap bank, these two are giving you the actual capacitance of the cap bank only, right? Everything else is more like parasitic. Of course, the varactor is a real one, it's not a parasitic one. So if you do all that, your total capacitance will come to about 500 femtofarad. So if this is your total capacitance, this is your L, you get an F max value. Okay, so that is the frequency of oscillation. Similarly, if I now increase my CT code and say, I have got, so this was the case where the lower 5 branches were on. 31 means, the lower 5 branches, LSB, then the next one and next one, so the first 5 are on. This means the 3 MSBs are on, rest 5 are off. The LSBs are off, 5 LSBs are off, and 3 MSBs are on. In this case, if I have a configuration like that, then I have got more capacitance turned on the cap bank. So cap bank will have more capacitance, but how about all the capacitance? So you have the core, same, buffer has not changed. Now the on capacitance has changed because we have huge amount of on capacitance coming, right? Each has 2.5 femtofarad, and now we have equivalent 224 of them. That gives you about 560 femtofarad is on. Off capacitance of the small tiny branches, they are also there. Varactor has remained the same, parasitic has remained the same, the inductor part has remained the same. So all of this comes to about 930 femtofarad, which gives you the F min as 5.2. Okay, so here we get F max and F min, and by doing all this, right, each and every part of it, the core, the inductor part, so what we have done is we have tried to find out all the possible capacitances which are going to be there in the VCO at different CT code conditions. And CT code is that 8-bit code I'm putting into the discrete cap bank. So based on that we have calculated it. Okay, so this gives you a framework for doing this, but now as you can see I'm not able to hit the target. Now what do? You play with it. So the way you play with it is, if you change the inductor, let's say for example, everything else I keep it the same and I change the inductor to 2 nanohenry, what happens? See, if I do that, everything gets adjusted and my F max is going to come to about 5.4 and the minimum is 3.8. It's not 3 and 6, that's what I wanted. Okay, so this is one thing which I will go back to this. I know the other thing that helps, and what helps the most is to get a better spread you have to go to the cap bank in order to change this unit sizes. So I'm going to put it 10. I'm going to say that the C unit which I started with 5 is not 5, it's 10. And also to maintain the Q, because you can see the Q is going down, the Q is going down to about that, I will also increase the size of the switch in the cap bank. So if I do that, it comes to about 6.2 and 4. Right, that's not good enough. Now if I say that I'm going to go to 15 with this as 3, so I maintain the Q, you can see this, the on and off capacitances are changing. It's changing this one too, right? F max and F min is also changing. And in this particular case, the design that I put together were actually based on these values in 65, and what I am able to get is roughly 5.2 and 3. So my lower end is 3, but my higher end is not able to go to 6, it's 5.2. And I actually had I think it gets about 5.3. So even though I started with a target of 6, I didn't get it, based on these calculations. There is more tweaking you have to do, which will be based on the VCO buffers. You might have to make it smaller to reduce some of the parasitic cap. Maybe you have to adjust the sizes a little because they are contributing quite a bit, but also you have to make sure that they can actually oscillate, if you make the sizes smaller. So doing all that, you would come to a point where you will adjust these variables, manually, and see what is the best you can do, right? In terms of how close can you come to your targets, and then you go to the simulator. So again, this was the target values. I've come to this point where it's 5.2 and this. Of course, I'm not using the complete CT code range, and I might be overly pessimistic in not using some of the codes which might be still possible over process variations. And again, that is something you can only find out over, when you simulate the whole thing. But with this kind of an approach, it has given me a starting point. It has given me the values of the inductor I want to use. You can even change the inductor a little lower, like it's easy to play around with it, and it will show you that, okay, I have gone to almost 6, but this has gone up. So now to increase the spread, I can go a little more. Let's see what could happen. So it's a little more, but as you play around, it will give you different values to start with, right? So that's the key point, is you have got a set of values that you can now go to the simulator, put together an initial circuit which starts with a set of values which should give you pretty close to these numbers. And when I put this in at least the 65 nanometer, it gave me pretty close to these numbers. Then you start tweaking it to see how you can tweak these different variables in the actual simulator to come close to the target that you've set in. Okay, so hopefully going through the spreadsheet, building it up this way, gives you an idea of how you could put together an initial design of the VCO quickly based on this approach. Something that I found very useful. I've been using it, and I just wanted to share with you guys. And you guys have any comments on it, feel free to send it to my email here. And also, if you need the spreadsheet, just let me know and I will forward it to you guys. Thank you for watching this video. Bye bye.